Hello, today we're going to talk about the beginnings of calculus and the historical context, why you would want to use calculus, and an example that doesn't involve calculus but shows you how calculus works. My name's Ian Wong, and today I'm going to talk about some math that I learned. The book that I am basing this content off of is Tom Apostle's Calculus 1, and it's from the very first chapter. And it's like in the introductory chapter. So what is calculus? Calculus is a tool that is a mathematical tool that's used for a variety of different applications. But what makes it so useful is it allows you to do two essential things. One is calculate how much of something there is, and the second is calculate how fast something's changing. And the most common kind of questions these relate to are like, if I have some shape, how much area is it? Like e.g. one, how much of something there is. And then the second thing is like, if I understand that something changes, like maybe it's like the population of like bacteria in a culture, what will it be however minutes from now? So you want to understand the rate of change at some point in time with respect to usually a direction. These are two geometric illustrations of those ideas, but they can extend to things that are more complex. Like, so you could calculate how much area there is, not in a 2D space, but in like a 3D space, for example, like the area of a sphere. But it can even extend to something that's like more abstract, like the idea of how much work does it require to move like a 10-pound weight up like your flight of stairs. And similarly, like with population change or something like that, like maybe you want to understand the rate of change as you fall towards the earth, and to do with gravity. So because of like these two central tools, they apply to things like physics-based problems, biology, and even just other areas of math that concern measuring things. Where did this all start off? It started off with primitive shapes. So there's like the idea of geometry, and you wanted to measure, and people were interested in measuring like how much space occupied these different geometrical shapes, these polygons. And there were ways, there were methods created to achieve this. What I'm going to walk through briefly is just one of the ways which people calculated the area of some shape, and we're going to take that exact same methodology and use it to walk through an example that conveys like almost the intuition behind how modern calculus works today. Along the way there, we'll briefly describe like some of the troubles that prevented people from just immediately making that jump from like this historical approach to like what calculus is today. Okay, we have a shape, it's a circle, we want to know how much space is inside of it. The method used historically by the Greeks was this method of exhaustion. The whole idea is that in order to calculate the actual area within of this shape, instead of actually doing that right off the start, instead there will be this approach of iterative refinement. So you make an approximation, and then you refine that approximation over and over and over and over until such a point where the approximation basically just becomes the thing that you're trying to calculate. In order to make that refinement, the Greeks relied on this understanding or intuition that if you increase the number of sides on a polygon, and then it will increase, then the area of the polygon that you've increased will get bigger and bigger and bigger. So rooting it back to the problem, we have a circle, we inscribe or put inside of it a triangle. And since it's such a simple shape and it has such few sides, typically that means it's really, really easy to calculate. So we can do base times height divided by 2 to calculate the area of a triangle. And that gives us like an okay approximation of the area of a circle. Obviously, like you can tell that there are a lot of that there's a lot of error here, right? But instead, we can improve this approximation by increasing the number of sides. I'll walk through a couple of these. So from square or triangle to square to pentagon. And all in all, like we can see that the area is being occupied more and more by the shape with more sides, and the amount that's uncovered reduces. The reason why this is called the method of exhaustion is because you're exhaustively applying the same iterative technique and exhaustively reducing the amount of error that is unaccounted for by the approximation. That's basically it. You keep on doing that, and eventually you find some sort of calculation that's pretty close to what the area of a circle is. Now, there are some shapes where this approach doesn't work well. For example, you could have a very weird shape that is not easily decomposed, and you might want to calculate the area of this. Using the approach that we talked about before, this slicing up the shape and then trying to apply that approach piecemeal does not work that well. Another example of how this wouldn't work is if you have some sort of complex, not in the complex plane, but you just have like some arbitrary curve that has a very odd shape to it, and calculating the area underneath that curve is not very easy. So there needs to be, we need an improved tool for those other use cases. And in order to get to that tool, historically we had to do a lot of stuff. There are 4 things. We needed a proper numbers, or we need a better way of writing numbers. So historically there was the use of Roman numerals, I, like IV, etc. And it was just a very bloated way of writing things, and it helped to have the Hindu-Arabic number system, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the things that we're familiar with today. It also helped to use a decimal system where we express numbers as powers of 10. So like every position you go to the left increases in magnitude by an order of 10. So you can compactly express things, and then when you're doing numerical procedures, it's very convenient to do math or arithmetic. The third thing that we didn't have was negative numbers. Historically speaking, you could express positive quantities, but the idea of expressing something negative was illogical and not accepted. Traditionally what that meant was that you would just, as you're doing your algebra, you would rearrange things so that they could only be positive, which doesn't work in all cases, but like that was the approach. So instead of like having like x plus y equals 0, you would not allow yourself to move this to the other side and become like a negative number. So number systems, we talked about decimal powers, and then there is negative numbers. If you're curious, you can look at number systems, and you'll see that there is a class of numbers that looks like this. and we needed to add these negative numbers in addition to the rationals, whole numbers, etc., so that we could properly do calculus. The last thing that we needed was stronger acceptance of just algebra and algebraic manipulations, like moving things from one side of the equation to the other by adding, like negating their effects on either side of the equation. And at that point, history started to see examples of solving like fundamentals in calculus, like for example, solving for the solutions of cubic and quartic functions by some of the Italian mathematicians. Hey everybody, so in the following proofs, I made a mistake while I was recording. I accidentally hid some of the work that I was doing underneath the webcam, and in the future I'll avoid it, but hopefully as what I go through is still useful. Okay, so we have all these tools now. We have the proper number system, we have decimals, we have algebraic manipulations, we have the method of exhaustion, and we want to understand how the basics of calculus work. We'll pick out integral calculus, which is calculating how much of something there is, not necessarily how fast things are changing. And we will use the method of exhaustion to walk through that example. I'm going to draw a diagram, and this diagram is going to be of a parabola. And what we're going to do is we're going to take, we will want to calculate a part of that parabola and how much area is underneath the parabola curve. So I'm going to freehand, hopefully, pretty well this parabola. And it looks something like this, perhaps. And let's say for some point, we want to calculate everything underneath this parabola. I'm just mirroring it on the other side. So in our case, what we want to do is, the question is, what is that? How much area is that? It's unlikely that there's an intuitive answer to this. Like we can't just like say it's like 5 or something like that. Like I mean, there needs to be some system for deriving this answer. And probably the best way to start off is by expressing or is by bounding what the possible answer could be. So imagine that we have wrong color. Imagine we have like some number line, right? And it goes from negative infinity to positive infinity. And what we want to do is pick out some number on this number line that represents this area, right? We don't know what that number is, but we can at least start off by saying, like, you know, it's bigger, or it's like this number here is smaller than the actual number, and that number is smaller than this other number. And at that point, having some sort of like range, we can begin to play around with the definition of that range, maybe making it tighter, maybe figuring out what are the numbers that can sit in between those ranges, and come to a number that come to the actual number that represents the area. Okay. So we'll start off by creating that bound. Let's first figure out this, perhaps. Let's figure out, what we want to figure out is this one right now. Let's figure out the lower bound. And one possible approach for this is to measure things in terms of simpler polygons, similar to the Greeks. So we'll take some rectangles, and we will inscribe them underneath the polygon, and they will all be of equal width, and they will look something like this. And you can see that as I go along, this occupies some of the space underneath the parabola segment that we want to measure. And but there is some degree of error, right? Like we can see right here, that there is like that our rectangles don't account for that space. Excuse me. Now let's do this exact same thing for sorry to pause. We have these rectangles, and the sum of the space occupied by those rectangles is less than the actual space occupied by the parabola. Hence, like these rectangles is this lower bound, right? Let's give these rectangles a name. We will call like the lower bound. Let's the lower bound be symbolized by Sn. Okay, now let's figure out an upper bound. We can take the exact same approach, but instead we will overshoot the parabola, and we can do that by terminating the rectangle after it exceeds the height of the curve, and then intersects it. Something like that. And now you can see that we also have similar error. However, it's in a slightly different position. So we've measured too much here. Let's call this the upper bound, right? Because the space occupied by the sum of the rectangles on this other side is more than the space occupied by this parabola. Let's give this a name. Let's call let the upper bound be symbolized as by Sn, capital S for upper, lowercase for lower. Now we have an upper and lower bound, and before taking things further in a meaningful way, we need to start describing things arithmetically. It's no longer useful to describe in terms of like visually or geometrically, like as we're doing on the screen. There's no more juice to squeeze, and no more information available until we start to quantify things literally. So let's do that. Let's begin by quantifying the lower bound. And we can do that by trying to calculate how much area this actually occupies. So we have a bunch of rectangles, and I guess the next thing we want to know is like, what is this curve? For the demonstration today, let's call this curve f of x equal to x squared. So it's just a quadratic equation. And what that means is if I have some point, for example, here, and this has an x value equal to perhaps 2, then what that means is that f of x is equal to the square of x, in this case 2, and the square of 2 is equal to 4, right? So if we find the x values of any of these rectangles at this point, etc., we can calculate how high the height of this rectangle. Excuse me. Using the x squared definition. The next thing that we want to do, so I guess in general, like what we're trying to attempt to do is we want to figure out what the area of that rectangle is. And in order to do that, in order to calculate the area of this rectangle, we need to know the length and the width of it, right? And as we were saying before, the length is equal to f of x. That is x squared. And the width, there's this question like, what is the width? We need to define that. So one thing we can do is we can say all these rectangles are of the exact same width. That makes it easier. And then we can say, well, we know that we need to measure the area underneath this parabola only up to a certain point. Like the parabola continues on, but we don't need to measure anywhere beyond that. And so we will take like this section of the parabola, and we will draw inside of it an arbitrary number of rectangles, n rectangles inside of it, and them all being of equal width. What that means is, like, if I have some width here, then if I draw n rectangles, to relativize this, if I have a width, a parabola width of b, and I have n rectangles, then each rectangle is of width b over n, right? It's just like if there's n rectangles that span the width b, then each occupies like a fraction or an nth of the total width. So now we know that the width is equal to b over n, right? And we know that the height is equal to x squared. So in order to calculate this, we need to still figure out what is x at this point, right? So as we walk this way, right, we know that up to here is b over n, right? If we walk some more, then this turns into 2b over n. And the more and more we iterate, this number increases to like 3b over n, and finally to nb over n. And so this gives us a way to figure out the x value for any of these given triangles. And because we know the x value, now we can compute the height of the triangle. So at this point, the height of this triangle is b over n squared, right? So if we were to write this out, this one would be like b over n squared. Maybe I'll draw it down here, b over n squared, and then 2b over n squared 3b over n squared, etc., where this corresponds to the height of this triangle. This one corresponds to the height of, sorry, this rectangle right here, and so forth. Okay, so let's calculate the area. Let's calculate the area of all these rectangles now, because we can do it for each one at this point. So we will say the sum of the lower, or we can use the sum of the lower bound rectangles, also known as Sn, is equal to in the first in the first case, I would, so there's this should actually be filled in. The first rectangle does not occur until b over n over, and the reason because of that is that it's impossible, like when the parabola hits 0, you cannot draw a rectangle greater in height than 0. Therefore, it has to be 0 for the first b over n. So yeah, this was just a graphical error, but so if we're gonna write this out, it looks like our width, which is b over n. So let's say that rectangle 1 equals b over n times b over n squared, right? And then we'll say that like rectangle 2 is b over n, because that's the width of the rectangle, times 2 b over n squared. And then we'll just repeat this a bunch of times. 3, dot, 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 and eventually you have rectangle n minus 1, and this equals n minus 1 The reason why we don't have n rectangles on the lower bound is for the very same reason that I mentioned about you cannot draw a rectangle that starts at the origin, because if you were, the maximum height of the rectangle would be 0, because the parabola intersects the origins like 0. And since there is no rectangle there, it's just equal to like the height is 0. That rectangle, that one of the rectangles of the n rectangles effectively disappears or becomes 0. That's why you have n minus 1. So now we have all these different rectangles, right? And our goal is to sum them. We want to add them all together, and that will give us the total area of the lower bound. We can literally just do that, right? And we can say that, like, using our terminology, Sn, well, maybe I'll just write this out in text, but Sn equals the addition of all this. So we can write this out quite literally, like b over n, like the first term, like term 1 plus term 2 plus term 3, but that's quite exhaustive, right? Instead, what we can notice is that there's a pattern going on here. There is b over n all the time, right? So we have this factor across all of the terms. We can factor that common factor out. The next thing that we notice is that there's this squaring function going on, right? So maybe let's simplify this. We will take this and we will take this equations and simplify it. So let's do that. Rectangle, and that will make it easier to add up is what I'm getting at. So b over n times like b squared over n squared. And if we were to simplify this, like rect 1 equals b cubed over n cubed, right? If we do this for rectangle 2, it becomes b over n times 4 b like 2 squared by b squared over n squared, and then that simplifies to b cubed over n cubed multiplied by 2 squared. And then if you're to keep on repeating this, you would find that there's a common pattern here. 3, 3, 3, 3 squared. So basically everywhere there is this b cubed over n cubed term and this like square part on the right. I'll just highlight it. So there's always this like b cubed over n cubed part, and then there's always these squares. And so when we're kind of simplifying all of this, what we can find is that if we just do b cubed over n cubed, and then we multiply and we factor that out, then it would just be like 1 squared plus 2 squared. I guess I'll drop this, plus dot 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 and so forth to n minus 1 squared. So this is our formula for calculating this lower bound. Now, if we were to do the same thing for the upper bound, it would be nearly identical, right? Except there's just one more rectangle to account for, because it's an upper bound to the parabola, and the parabola intersects at origin 0. The rectangle automatically is greater than 0 because it's an upper bound, and therefore there's one additional rectangle in the number of rectangles that we've inscribed, and that's n minus 1 plus 1 is n. So what we can say is that S of n, which is our upper bound, is the same formula, b over n cubed, and then like 1 squared plus 2 squared same thing. So this thing is this number, and this thing is this number right here. Our lower bound and our upper bound. And so we still want to know what this is. We can formalize this instead of like drawing it as all squiggly lines, instead as something that looks like this. Sn is smaller than A, which is smaller than S of n, where A is the area of this underneath the parabola. now that we have things arithmetically defined, we can employ some algebra to start to elucidate, find more information about these upper and lower bounds. The very first algebraic manipulation we're going to make is to replace these square terms with something that is simpler. We need an analytical way or a closed form way, an equation that allows us to calculate the sum of squares without literally writing out all the terms. And that compact form may help us to make further algebraic modifications that will allow us to actually calculate this number. So, like, what is the sum of squares? There is a formula for this, and and we'll derive it in order to actually figure out what the area of the parabola segment is. So goal is to determine analytical function for the sum of squares. This is what we want to do. And let's derive it. And we will begin the derivation using, by starting off with this formula of a cubic power, or of the cube of some variable plus 1. So here is the initial formula I have, and what we'll find is that if we rework this, we can express the sum of squares. So k plus 1 by k plus 1 is k squared, right? K by k is k squared, and then k by 1 is k, and then 1 by k is plus k, and then 1 by 1 is plus 1. I'm just doing binomial expansion on these two terms, like k by 1, 1 by k, and then 1 by 1. And then we do expansion again between these two terms. So k by k squared is k cubed, and then k by k is k squared, k by k is k squared, and then k by 1 is k. And then we add that to 1 by k squared, which is k squared, and then plus k plus 1. Simplifying is k cubed plus 3k squared, 1, 2, 3, plus 3k, 1, 2, 3, plus 1. Now that we've expanded this formula, let's rework it. And the way that we will rework it is by expressing a similar idea as the sum of squares, but instead we'll do the sum, or we'll do express the differences between cubes. So if we move this term to the other side, minus k cubed, what we now have is the difference between cubes, k and k plus 1, is this value. So we will call this the difference between cubes. Cubes of k plus 1. And now what we're going to do is evaluate. I'm just going to expand our canvas here. But what we want to do is evaluate the difference of cubes at different values of k. So here's our formula. Let k equal 1. And we'll say that this turns into 1 plus 1 minus 1 cubed by 1 1. And then if we do the same thing for, we'll say this like, let k equal, just more concise, k equals 1, k equals 2, 2, da 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 da. And if we keep on doing this, I'll actually draw out one more. If we go all the way up to n, we will have a bunch of different equations that look very similar to one another. And there's actually a nice kind of trick here that allows us to derive the sum of squares. And I will show you it. So you'll notice that if we add up all of these terms again, we, on the left-hand side, will get the sum of the difference of cubes, right? And rather than writing out like this term plus this term plus this term, etc., we can begin simplifying before we actually even add it up. And 1 plus 1 is 2, so 2 cubed, plus 2 cubed, minus 2 cubed, plus 3 cubed, minus 3 cubed. So these terms negate one another. Like this one negates this one negates the one that would be here, and then this one would negate the one that's here. And all that we're left with on the left-hand side is n plus 1 cubed minus like 1 cubed equals some value on the left, which is pretty cool. So that's been compacted on the left side. So we are done with this, right? We're done with this section. We also know that there's patterns on this side. So there's this sort of pattern where it's 3 times some increasing number and like the square of that number. We can factor this out, right? And express this as like factorize out the 3 because it's common to everything, and then express the squares inside of the factorization and squared. So now we have the second part where like this corresponds to this corresponds to this right here. The next section we'll tackle is this part right here. Again, common to all terms is the 3, so we can factor that out. And this will be plus 3 times like 1 plus 2 plus 3 plus n. Now we have a way of simplifying this. And the last part is the plus 1s on the far right. And since there's like n different equations, like 1, 2, 3, 4, 5, all the way up to n, we know that this will sum to n1s or plus n. So, whoa, I just lost my mouse. this corresponds to this. So we're at a point now where we have the different, like we have summed the difference of cubes. We have the quantity that this equals on the right side. But if we look carefully at it, we can notice that there is the sum of squares here. And so if we rearrange this equation and isolate for this term, we will have an equation that tells us how to calculate the sum of squares. And then this will allow us to, this equation will allow us to simplify our upper and lower bounds. Let's do some more work on this. Let's simplify and rearrange for the sum of squares. Before we go about moving around terms, we can begin by simplifying this term right here, 1 plus 2 plus 3 plus 4, all the way up to n. And we can actually derive this as well. Lots of derivations. But one thing that you might notice is if you have n segments this way, right? And then you have, you draw like a block of 1, you draw a block of 2, so this is like equal to 1, 2, etc., 3, and you keep on going, all the way up to like the last block here, which is n. There's a nice trick, well, first off, like this whole area here that would be defined by all these rectangles is equal to like this sum, right? So that's how we draw it. But if we start to do things like add 1 here, 1, and we know that this one is like n minus 2 or whatever, then we add 2 here, and this is 2, and then we add like 3 here, etc. You know that, like, you will begin to notice that this kind of algorithm will yield a perfect like rectangle. And as you decrease the size of n and increase the size of the other side, it occupies all of the space here. And so since we know that the height of this is n plus 1, and we know the width of this is just n, therefore the surface area of this rectangle is equal to n by n plus 1, right? And since we know that each side, like this top side and then this bottom side, occupy exactly 1/2 each because they're duals of each other. They're the opposite. Like they're just they're the same shape that's been flipped and then concatenated to one another. So sorry, like you like flip it and then sandwich it together. That therefore the area of like half of this, or like this area, everything in here, is n by n plus 1 over 2, which is equal to this right here. Okay, let's rewrite this out then. N plus 1 cubed minus 1 cubed equals this very long term, plus 2 squared plus n squared plus 3 times, I'm just going to drop this a bit, n by n plus 1 over 2 plus n. And let's further simplify this. We can expand this internal expression to n squared plus n over 2. And then we can further expand this to 3n squared by 3 over n. And now at this point, we can start rearranging. So if we bring this n over, actually, sorry, I made a calculation error here. Instead of having n equations, let's instead have n plus let's have n minus 1 equations, and it'll make this calculation a little bit easier. So if we were to do that, adjustment, instead of having n equations, have n minus 1. So this would change to just n cubed because it's the minus 1 part. This would change to n minus 1 squared. And then this would change to 3 times n minus 1 by n divided by 2. Because, and this evaluates because n minus 1 is on the left-hand side, but n minus 1 plus 1 turns into n. So n minus 1 by n is the final equation here. And then plus n minus 1. Okay, let's simplify some more. So n squared minus n. Let's move this n minus 1 term on the far right over. We'll move this over. So subtracting n by n minus 1, n by n minus 1 turns into minus n plus 1. And at this point, the left-hand side, like this minus 1 plus 1 term cancels out. And we have something that looks like this. Okay. And now let's simplify this part. So 3n squared over 2 by minus 3n over 2. And let's rearrange some more. Pull this term over. Plus 3n squared equals this value. And then let's pull over the next term. Right? And minus this term. And then at this point, oh no. Okay, I deleted everything, but that's really unfortunate. Yeah, that's unfortunate. Okay, so anyway, we'll continue because I had the last in my copy buffer, but we'll continue this pattern, and then 3n over 2. This is a square term, so we can't combine it, but we can combine this. So it's negative n plus 1.5 n. And that will just yield half, like half n over 2. Okay, now let's simplify. We will divide by the factor of 3. So 3n squared over 2 divided by 3 is just the same thing without 3. N over 2 divided by 3 is n over 6. And then n cubed over 3 is that. So now we have a formula which says that this is equal to the sum of squares all the way up to n minus 1. There's actually a really easy way to make this, to extend this formula to n squared, and it's by adding n squared to both sides. So if I add n squared to this side, right, generalizing to n squared, if I add n squared to this side right here as this term, and then I add n squared to this side right here, and then I simplify, I'm going to have the equation on the left as representing the sum of squares to n squared, which is what we want. So negative n squared divided by 2 plus n squared is just so negative a half plus 1 whole is just positive 1/2. So just change this. And that's our formula. This is our derivation, or our closed form analytical representation of the sum of squares. So that was a lot of work, and it involved a couple. We need to do a derivative to calculate the derivative for our proof, but luckily we can say that sum of n squares equals this. So we had the original equation, or inequality, which was that the lower bound was smaller than the upper bound. We expressed the lower bound as being arithmetically equivalent to b cubed over n cubed multiplied by the sum of squares all the way to the n minus 1 term. And we know that the sum of squares is equal to a closed form variant, which is n cubed over 3 minus n squared over 2 plus n over 6. We also know that the upper bound is basically the same thing, but with an additional n squared term at the end, and they look somewhat identical. So n cubed over 3 plus n squared over 2, because the n squared to the original formula here just flips the sign, and then n over 6. So now that we have these two arithmetic representations of the formula of the inequality, we can write a simplified variant of that inequality, and it's like that a is less than this upper bound, and that this lower bound is less than the upper bound. I just need to modify the sign here. And there's one simplifying step that we can, more simplifying step that we can take, and it's to replace a with something. We can actually argue that this term and we can simplify this. We can actually argue that if we take this value, that this value is actually smaller than n cubed over 3. And we can also argue, so like this is argument 1, and we can also argue that argument 2 is that this value is greater than n cubed over 3. And we can argue these two things. And then if this were true, if they were true, then we would also be able to argue that like this, like lower bound is smaller than n cubed over 3, which is smaller than, like I'm just concatenating these two, which is smaller than this. And if that were true, then if we multiply by n cubed over, or b cubed over n cubed to each side, then it would be this thing, this whole, like basically rewriting this whole thing, is smaller than b cubed over n cubed multiplied by n cubed over 3. And if we simplify all of this, this just turns into Sn, which is smaller than b cubed over 3, which is smaller than the upper bound. In order for, so like this, if we could argue all these things, then we would have a simplified inequality that looks like this. And at the very least, we could say that b cubed over 3 sits between the upper and lower bound, and a may equal b cubed over 3. But in order to make this argument, we actually have to prove these two things, that n cubed over 3 is indeed smaller than this term, which, and we also have to prove the second one. If we look at this one, we know this is immediately obvious because there is this additive term on the right. There's only a positive number, can only be positive, and these two terms on the here and here are identical. Therefore, this side must be true. So we can accept this one as proven, but we need to prove this one. It's unclear whether the n cubed term on the right-hand side is always greater than this left-hand terms, because there is like a negative quantity being subtracted from the this n cubed term, and then a positive term being added. And while we can argue that you could argue that look, there is a quadratic here and there's a linear equation here. The quadratic's going to always exceed the linear equation, especially since like these reductions are the reduction on the quadratic is by a smaller factor divided by 2, and the reduction on the linear equation is a greater number. Therefore, like what I'm trying to say is that these divisionary terms are irrelevant and they don't matter. And because of that, this negative term is always going to be greater than this positive term. Just remember that these equations and the formula we're trying to calculate, like the area under a parabola, is for when we have rectangles that are greater than or equal to 1, because we're taking that area, area of the parabolic segment and dividing it up into multiple rectangles. So this holds true, like, because we don't have to deal with the case where x squared is less than or equal to 1, or less than 1, right? Which would make this statement not true. So anyway, long story short, we could argue it like that and say that this is true, or we can prove this part using an inductive proof. And that's what I'm going to go on to show you next. So I don't well understand inductive proofs, but you can use an inductive proof to show this inequality is true. The way that I would best describe inductive proofs is that there's this inductive process, there's this thing that induces something else, and ultimately where we're going with this is that similar to numbers or integers, we know that we can reach any integer by progressively incrementing a smaller integer. So like if I start with 1, I can eventually get to 1 billion if I want to, by just adding another 1 and then adding another 1. And basically what I'm trying to say here is that we can achieve something by incrementally making changes, and the inductive proof follows that takes inspiration from this, and it shows that if there is some state at which I can begin, and then I can show that I can incrementally make changes, then and those changes will be valid and true, then due to the ability to increment, the thing that I'm claiming will also be true, because this will carry forward and render the same results to the thing that I'm trying to prove. In our case, we want to show that for any arbitrary n minus 1 or n, that this inequality holds true. So we have some function that says a of some value x, and that this will hold true x minus 1 for t squared, whatever, is smaller than x cubed over 3, right? So this is the thing that we want to demonstrate, and we want to show that this is incrementally true, but we also want to show that it actually is possible, or it can actually occur to begin with without even showing that it's incrementally possible. If it were possible, we just want to show that it is what is possible. So we'll take a of 1 in this example, and this equals the sum of 0 by t squared to 1 cubed over 3, and the sum up until 0 is just 0 and then 1 over cubed. If we are kind of irked by how the sum of 0 works, you can just do a different number, a of 2, and then the sum of 2 minus 1, which is just 1 of t squared, is smaller than 2 cubed over 3. That will result in 1 squared being less than 2 cubed over 3, which is true, right? 8, to be explicit, 1 is always less than 8 over 3. So in 2 cases now, we've shown that there is there's grounds to even talk about this sort of incremental relationship, because it actually can occur in the first place, right? And for example, when n is 1 or n is 2. And now we need to show that this incremental behavior is actually true. We will show that over here. And we will take a of k, which means that, well, I'll probably actually just write it out. So a of k is this thing, and it says that k minus 1, the sum of k minus 1 is less than k cubed over 3. And then the thing that we're trying to prove, like we'll assume that this is true, and then what we want to prove is if k is true, and we know this to be true, right? Because we've shown it for version 1, and version like when n is 1 and n is 2. So at least in some cases this works. And then we want to show that this then holds for this case, x squared, and then it's k plus 1 cubed over 3. So this is what we want to demonstrate, or this is the thing that we want to, the behavior we want to prove. We can show this to be true by instead taking this thing that we know to be true and slightly modifying it. So a of k, and then we will take the same thing, k minus 1, x squared. We will add k squared to the left side. And then we'll have k cubed over 3, which was the same term right here, and add k squared to the left side. And because we know this was true to begin with, this is also true because we're giving equal treatment plus k squared to both sides. And then, so this is a reliable statement. This is true. That's supposed to be a check mark. This is true. And all we have to do now is show that this, if this is smaller than the thing that we're trying to prove, this, then this statement is also true. So we can do that. Again, k cubed over 3 plus k squared is less than k plus 1 cubed over 3. So is this actually true? And we know this to be true because of the form of proof we did earlier. Right here, if we take, which I'll demonstrate by copying this and pulling this all the way down here. Whoa, where'd it go? So we know this proof to be true, right? And if we divide, so k plus 1 cubed, divide this by 3, and then divide this by 3, well, then we end up with like this part matching this part right here. But on the right hand side, we get k cubed over 3 plus k squared plus k plus 1/3. And we know that this amount, like this right here, is, as we can see, is bigger due to these terms than this amount here. And because of this, we can show that this whole statement holds true. And because we know that this side is bigger than this term, that therefore this conjecture that we have that k plus 1 holds for this inequality is true, because this number on the right side here is bigger than the explicit expansion that we did down here. Okay, so we showed that iteration is possible. we show that the iteration, while like theoretically might mean something, is actually can actually occur in A1 and A2. So we've shown possibility of occurrence, we've shown the possibility of iteration, and therefore by iteration we have proven that this statement holds true regardless of n, where n is like greater than or equal to 1. Sorry. So ultimately what we wanted to show was that the lower bound and the upper bound sandwiched this b cubed over 3 term, and we wanted to arrive at like what is the actual value that sits between the lower and upper bound. Is it b cubed over 3, or is there more than one value? In this representation where the upper bound and the lower bound is like a factor of b cubed over n cubed multiplied by the summation itself, it's not very tractable and it's hard to determine like what those actual values are. But at least we know that this is like the true bounds, and b cubed over 3 can actually be here, as proven by the inductive hypothesis we did, to show that like at least on the left hand side that the n-1 summation is indeed less than n cubed over 3, yielding by multiplication b cubed over 3 after we multiplied by b cubed over n cubed. So we know this is true. It's not very useful. We can make it more useful by taking the lower bound, b cubed over 3 somewhere here, and the upper bound of Sn, and instead changing this upper bound and pushing it out to some other value, and taking this lower bound and pushing it out to some other value that is like less precise, but still holds true on the inequality. And if we can push it out, if we can adjust these values, there may be some analytical observation that we can make that will allow us to talk about b cubed over 3 being the one or one of the many solutions. So the key kind of finding that will allow us to do this is the n cubed over 3 relationships. We know that n cubed over 3 is smaller than the sum of n-1 squared, this like that summation. And we also know that this is smaller than the same summation but for n. And because of that, we can leverage this kind of relationship to further extend out the Sn, the lower bound. And remember that like the lower bound is this very term multiplied by b cubed over n cubed. This is the definition of Sn. So if we replace this term in that definition with something that's bigger, like that's greater, we will have something, we will have like Sn being smaller than like whatever the new variant of like this is by b cubed over n cubed. And that will allow us to get us this thing. So we can take advantage of this by, we can find a bigger number by utilizing this inequality, right? So if we know that the n-1 square is less than n cubed over 3, we can So actually, sorry, we'll use the we'll use this instead. Since we know that this is true, if we take n cubed over 3 and we minus n squared from it, and then we do likewise for the sum of squares on the right side here, n x squared minus n squared, this results in this useful relationship. N cubed over 3 minus n squared. So we know that this number is smaller than this number, right? And this summation is the same summation that's being used right here. So if we sub in this number here, then this will yield us a term that's less than Sn, which is like the smaller lower bound here. So let's do that. We'll do n cubed over 3 minus n squared, and then this whole value multiplied by b cubed over n cubed is smaller than Sn. We'll spend a couple seconds just simplifying this because we'll end up using it later. But if I were to expand this, it would be like b cubed over, and then the cubes cross out, right? So it's b cubed over 3 minus b cubed over n, which is smaller than Sn. If I do this for the right side, if now we want to extend out this upper bound to something that's a little more tractable, we can do that by making use of this relationship here, where like the square of up to n minus 1 is smaller than that. I'll just copy that here. So we have this, n minus 1 square is less than n cubed over 3. If we add like n squared to both sides, we end up with n cubed over 3 plus n squared. And then like this boils down into something that we're already familiar with, which is the sum of squares up to n being smaller than this number. And then we can then, and this representation allows us to then show that like if we multiply by b cubed over n cubed by the sum of squares, which is the like upper bound, it is less than this term on the right hand, over 3 plus n squared. And just to be explicit about this, right, like this term right here is equal to S of n, and so S of n is smaller than b cubed over 3 plus b cubed over n. So now we have here and here are two extended bounds. And to draw this out, it looks something like b cubed over 3 minus b cubed over n is smaller than a, which is smaller than the right b cubed over 3 plus b cubed over n. A looser bound on the area of A, and before we had a more precise bound, lower and upper bound, which is the b cubed over 3 by n cubed multiplied by 1 squared plus n minus 1 squared, which is smaller than a, which is smaller than the same thing. Which is the same thing as saying Sn is smaller than a, which is smaller than S of n. So we have this expanded definition, and we know that a possible value of a is b cubed over 3, meaning something that looks like this. So this still looks like it holds true, right? Because negative this term is smaller than the b cubed term, and adding that term makes it bigger than this term. And the final thing left to do is to show, can a be b cubed over 3? Can a be less than b cubed over 3? Can a be more than b cubed over 3? If we, I'll write this out. Can a be 1 b cubed over 3, 2 less than b cubed over 3 is less than b cubed over 3, or 3 a is greater than b cubed over 3. Let's assume we'll make an assumption, and we will prove that a can only be equal to b cubed over 3. But first, let's assume that a is greater than b cubed over 3. Then what this means is if I took a and I said a is smaller than b cubed over 3 plus b cubed over n, and then I work this formula according to the assumptions that we just made to simplify it, then it's like a minus b cubed over 3, which is possible because a is bigger than b cubed over 3. Then this is smaller than b cubed over n. And then if I multiply this term on the right hand, I end up with b cubed over 3. And then continuing this this forward, if I divide both sides by a minus b cubed over 3, we can see that what this suggests is cannot be true. N is some as n goes towards infinity, the right hand side here, it remains a constant number, and therefore at some point infinity will be greater than c. That's why this can't be true, because b is of a constant width. Remember, it's the width of the parabola segment we're trying to measure. This is valid because a is bigger than this number by our assumption here, which means we're not dividing by 0. So we've proven that a cannot be bigger than b cubed over 3. The same exercise applies when a is less than b cubed over 3. You can show that as like n increases to negative infinity or whatever infinity, that this same consequence happens. Given that, these two are impossible, and the only possible solution is b cubed over 3, because we know it, like this upper bound and lower bound actually like holds true by the obviousness of its of the equation. Therefore, like what we can conclude, therefore b cubed over 3 equals a, the area of the parabolic segment. So this right here, the area underneath the segment is always b cubed over 3, whatever you define b as. Like this could be like 5, for example, and this could be 125 over 3. So that is how to calculate the area underneath a parabola using using a method of exhaustion, where you basically increase the number of rectangles and get finer and finer number of rectangles, which get closer and closer to estimating the parabola.